The following content is provided under a Creative Commons license.
But neurons have a soma or a cell body. Those are what make up the gray matter when we look at the brain. They have an axon that can be covered with myelin that makes the white matter. The dendrite is the extensions of the neurons that have the input to the neuron. We know that neurons communicate by neurotransmitters across synapses, junctions between different parts of neurons. When you have a collection of cell bodies, people call it a nucleus. When you have a collection of axons, they call it a tract. It's just vocabulary and stuff. And you know this from other courses, just reminding you about them. And then you get these unbelievably startling kinds of numbers, which are always huge estimates, but they show you how amazing your brain is, okay? And how hard it is for us to deeply understand how the brain works. I mean, we understand incredibly more than we did 10 years ago, 20 years ago, 30 years ago. We're incredibly far from understanding how your brain accomplishes the amazing things it accomplishes. So it has about 100 billion neurons. It has about 100 trillion synapses, connections among neurons and dendrites. If you were to lay out the very thin myelinated axons in your brain, just the big axons that get myelin, it's estimated that you have 62,000 miles of axons. Okay, that's pretty good, right? Now you really want to wear helmets when you go skateboarding or anything, right? And about 100,000 miles of dendrites in each of you, right? So this is why the brain is amazing and hard. It's fantastic in its complexity. An average neuron may have up to 15,000 connections, 1,000 synapses, and to 1,000 neurons. There's different ways of thinking about the computational power of a neuron, but they estimate that these might have, each one, the computational power of something like a medium-sized computer. So it's not the best computer, but you've got 100 billion of them. Okay? Now, that's the easy part, to get 100 billion neurons in your computers in your head. The hard part is to get them all working together efficiently, and you're not sitting around going, Computer 33, get up to speed here. We have to, something's wrong here, right? You don't even think about them. You just go about your business. The time for information to go from neuron to neuron is pretty slow compared to fast computers, pretty fast for biology, 10 milliseconds. And everybody thinks the secret of the brain, whatever it will turn out to be in many ways, is that you can run a fantastic number of computations simultaneously and collaboratively. But we don't have a deep understanding of how that all plays out. So here's a cartoon of this amazing axon, the cell body, and the dendrites to get inputs to it. The axon is the output signal of a typical neuron. Neurons can have these beautiful arborizations, tree-like properties of dendrites. Neurons have all kinds of different shapes in different parts of the brain, presumably reflecting their different missions, what they have to accomplish. An incredibly complicated cellular factory inside all of them, is producing different things. And this is a big overview. This is not for you to learn a specific fact. And here's an actual neuron that's injected in the fantastic tree of connections it makes with other neurons to accomplish its mission. Here's a cartoon of a synapse, the places where neurotransmitters a signal from one axon to one dendrite, for example. And here's an actual picture of, here's the package of vesicles that have the neurotransmitters in them, making a connection or synapse onto a dendrite. And you just have a fantastic number of these. And you're sitting in you right now, an unbelievable amount of stuff is going on, releasing them, cleaning them away so they don't hang around too long, building new ones to get ready to go. It's just an unbelievable story per neuron, never mind the whole of them.